When it comes to hunting for enigmatic objects in the early universe, the James Webb Space Telescope is quite the cosmic detective. Under the gaze across space and time of NASA's celestial Sherlock Holmes, we found a slew of fascinating objects dating just a few 100 million years old after the Big Bang. Stars and star clusters exist in abundance. Galaxies with perhaps up to 1 billion stars light up the universe. Even quasars with very large black holes formed early on, well before the universe was even 1 billion years old. It's the old chicken and egg problem made new. If there's a maximum rate at which black holes can grow, and the universe wasn't born with them, how did we make the ones that we see? In other words, how did the universe make such ultra-massive black holes in such short periods of time? And now, after decades of conflicting stories, scientists finally think they know what happened. But I warn you, that will blow your mind.
It is a crazy idea, and I admit it's a crazy idea. The trouble is, it seems it's quite likely it's true.
Join us as we dig deep into how James Webb's supermassive black holes actually arose. Just 50 to 100 million years after the Big Bang, the very first stars of all began to form. Massive gas clouds started to collapse. But because they were made up of hydrogen and helium alone, they struggled to radiate heat away and dissipate their energy. As a result, these clumps that gravitationally form and grow need to get much more massive than clumps that form stars today, and that has repercussions for what kinds of stars form, as well as what kinds of astrophysical processes occur alongside their formation. While today, typically, we form stars that are about 40% the mass of the Sun, the very first stars were about 25 times more massive, on average. Because the matter that leads to these stars, streams of gas, need to cool in order to collapse, it's only the largest, most massive clumps that form early on that will lead to stars. The average first star might be 10 times as massive as our Sun, with many individual stars reaching hundreds or even thousands of solar masses. In addition to these effects, there are cold, flowing streams of gas that collide and intersect, creating regions of dense, cold, neutral matter that rise up to tens of thousands, or perhaps even hundreds of thousands, of solar masses. There's long been a tension in cosmology between what's expected and what's observed. Are the black holes that form at the centers of galaxies made from the mergers and growth of stellar remnants alone? Or was there a different mechanism at play, such as either the formation of primordial black holes that the universe was born with, or from the formation of large seed black holes that arise independently of stars and stellar cataclysms? Let's first consider the from stars and stellar remnants alone route. Most of the first-generation stars that form will end their life in a supernova, leading to either a neutron star or a small, low-mass black hole. But without any heavy elements at all, the most massive stars will reach such high temperatures in their cores that photons, the individual particles of light, can become so energetic that they will spontaneously begin to produce matter and antimatter pairs from pure energy alone. You may have heard of Einstein's E equals mc squared, and this is perhaps its most powerful application. A pure form of energy, like photons, can create massive particles so long as the fundamental quantum rules governing nature are obeyed. The easiest way to make matter and antimatter is to have photons produce an electron-positron pair, which will happen all on its own if temperatures are high enough, and happens in some of the most massive stars even today. In these ultra-massive stars, as in all stars, gravitation is attempting to pull all of that matter in towards the center. But photons, and all of the radiation produced in the cores of these stars, pushes back and holds the star up, preventing its collapse. This happens independent of the star's mass, as that balance point must be achieved inside any object that isn't going to vary, oscillate, collapse, or explode. However, in these most massive stars, the radiation pressure is higher, the temperatures are higher, and the high-energy processes that occur are more numerous, including this phenomenon known as pair production. But when you start producing electron-positron pairs from these photons, some of that radiation pressure drops, as photons, which move at the speed of light, exert a greater amount of outward pressure than massive particles that move at speeds slower than light. Rising up to a temperature great enough to produce these electron-positrons pairs also depletes your star's ability to hold itself up against gravitational collapse. And while it's true that there are a few narrow mass ranges that lead to the star destroying itself entirely, a large fraction of cases will result in the entire star directly collapsing to form a black hole. The direct collapse scenario that has been observed in a few incidents, even in the late-time universe. This is a remarkable step. It means that the most massive stars of all, with many hundreds or even thousands of solar masses, can form when the universe is just 100 million years old or so, less than 1% of its current age. These stars will burn through their nuclear fuel the fastest, in 1 or 2 million years, tops. And then, their cores will get so hot they'll start turning photons into particles and antiparticles, which causes the star to collapse and heat up even faster. Once you cross a certain threshold, all you can do is collapse. And this isn't just theory either. We've actually seen stars directly collapse without a supernova, leading directly to what could only be a black hole. But that's only the beginning. Whenever you have a large cluster of massive objects acting primarily under the force of gravity, different objects get kicked around from these interactions. The least massive objects are the ones that are the easiest to eject, while the most massive objects are the toughest to eject. As these stars, gas clouds, clumps, and black holes dance around, they undergo what's known as mass segregation. The heaviest objects fall to the gravitational center, where they interact and can even merge. All of a sudden, instead of a few hundred black holes of a few hundred or a few thousand solar masses, you can wind up with one single black hole of approximately 100,000 solar masses, or even more. Remarkably, that might not even be the fastest way to grow a massive seed for a supermassive black hole to form out of in our cosmic history. Just as massive enough stars can directly collapse to a black hole without a stellar cataclysm, it's thought that a dense, massive, and cold enough population of gas can directly collapse to a black hole, perhaps even without a single star at all as an intermediary. This scenario recently got bolstered by an unexpected observation, made by combining both NASA Chandra X-ray data and James Webb Telescope data of galaxies from the ultra-distant universe. In Webb's data, a distant, faint, low-surface brightness galaxy was found from around 500 million years after the Big Bang, a galaxy that contains only around 10 million, maybe up to 100 million, but not more than that, solar masses worth of stars within it. However, in this galaxy, an active, feeding, X-ray emitting black hole of around 9 million solar masses exists, which raises new questions about where black holes came from. The big issue is that we've already seen large, relatively grown-up black holes even in the early universe, of hundreds of millions, or even over a billion solar masses after just several hundred million years of cosmic evolution. These black holes can grow in bursts that typically exceed the maximum rate of growth, or the Eddington rate that's sustainably allowed over long time periods. But if we trace that growth back to when we need a seed to grow from, those seeds must have been tens of thousands or even hundreds of thousands of solar masses to begin from. Starting from a stellar mass seed won't work. You might think to take the black holes from a single star cluster, merge them together, bring other star clusters with their own black holes in, and have them merge as well. But even that can't grow what we call an overmassive black hole, or a black hole whose mass is comparable to the mass of all stars within a galaxy combined. The fact that such a galaxy exists tells us that no, merging stellar mass black holes together, even en masse, can't be the sole way that we made supermassive black holes in the universe. Some sort of massive seed, more massive than standard star formation allows for, is required. One theory is that these black holes got a head start in their mass accretion processes by growing from smaller black hole seed. And early supermassive black holes could have grown from heavy seed black holes with huge masses around 100,000 times the mass of the Sun. These would have formed directly from the collapse of massive clouds of matter, thus skipping the star stage of other black holes entirely. Astronomers refer to such black holes as direct collapse black holes. These direct collapse black holes could then grow alongside galactic mergers, which were commonplace in the early universe, that would also bring supplies of gas and dust for these voids feast upon. Then eventually, other black holes might have collided and merged with those. John Reagan, a research fellow at Maynooth University, compares this to the 6-foot-tall toddler being born with a length of 3 feet. It is still a bit confusing and perhaps a tad disturbing, but it better explains how the toddler reached the size of an adult so rapidly, at least more easily than if the toddler started off with the length of an average infant. Regardless, the authors themselves point out the limitations of their research and urge caution with extrapolating that the growth of the black hole captured by James Webb reached supermassive status. A very interesting idea came from Nobel laureate Roger Penrose. The impossible supermassive black holes could be the black hole of the previous universe that created our universe. In the simplest possible terms, Sir Roger Penrose believes that our universe is not the first, nor will it be the last, to spawn from a dense mass of highly ordered everything into the complex universe we see around us. The current Big Bang model, which is partially grounded in inflation, doesn't supply a reason as to why a low-entropy, highly ordered state existed at the birth of our universe. That is, unless things were set in motion long before the Big Bang actually occurred. In Penrose's theory, our universe has and will again return to a state of low entropy as it approaches its final days of expanding into eventual nothingness, leaving behind a cold, dark, featureless abyss. By virtue, black holes, the vacuum cleaners of our universe, which leak radiation and destroy everything they touch, spend their cosmic lifetimes working to scrub entropy from the universe. As the universe nears the end of its expansion, the remainder of its black holes will evaporate or gobble one another up, thus setting things back into a state of order. During this period, the universe would begin to revert back into a similar state it was in at the Big Bang, when the geometry of space-time will become smooth again, which is in stark contrast to its current jagged form. According to Penrose's model, this will usher in the new aeon, after the universe is no longer able to expand any further, so it collapses back in on itself as a highly ordered system, one that is ready to trigger the next Big Bang. The current model of the universe says that any temperature variations in the cosmic microwave background should be random, but Penrose claims that he and his partner Vahe Gurzadyan, who hails from the Yerevan Physics Institute in Armenia, have found more than 12 very clear concentric circles within the data, which was collected by NASA's WMAP satellite over the course of a 7-year period, where there are regions where the radiation have a much smaller temperature range. To him, these posits are spherical evidence of the gravitational waves, massive ripples in space-time, that are created through the collision of massive black holes, which took place during the previous aeon. Of course, if his hypothesis, which has been dubbed conformal cyclic cosmology, were validated, it would suggest that the current state of our universe is merely one of perhaps an infinite number of aeons, which also means there is no need for a precursor for the Big Bang, and the remote future of the previous aeons somehow becomes the Big Bang of our aeon. While Penrose's theory has been criticized amongst other physicists, it's still an interesting hypothesis, with vast implications. After all, one thing can't be denied. Black holes are one of the most mysterious and interesting marvels in the macrocosm that always fascinate our minds. And in an effort to lift the veil on the most extreme thing in the universe, astronomers have spotted flares and echoes coming from the supermassive black hole at the heart of the Milky Way, Sagittarius A star. These cosmic fireworks and X-ray echoes could help scientists better understand the dark and quiet cosmic titan around which our galaxy orbits. The team of Michigan State University researchers made the groundbreaking discovery while combing through decades of data from NASA's Nuclear Spectroscopic Telescope, Array Telescope, or NuSTAR for short. 9 large flares the team discovered coming from Sagittarius A star had been caught by NuSTAR, which has been observing the cosmos in X-rays since July 2012. These signals had previously been missed by astronomers. According to team leader Shou Zhang, an assistant professor at Michigan State University's Department of Physics and Astronomy, we are sitting in the front row to observe these unique cosmic fireworks at the center of our own Milky Way galaxy. Both flares and fireworks light up the darkness and help us observe things we wouldn't normally be able to. That's why astronomers need to know when and where these flares occur, so they can study the black hole's environment using that light. Supermassive black holes like Sagittarius A star are believed to exist at the hearts of all large galaxies. Like all black holes, supermassive black holes with masses equivalent to millions or sometimes billions of suns are surrounded by an outer boundary called an event horizon. This marks the point at which the black hole's gravitational influence becomes so intense, not even light is fast enough to match its escape velocity. This means the event horizon acts as a one-way light-trapping surface beyond which it is impossible to see. Thus, black holes are effectively invisible, only detectable by the effect they have on the matter around them, which, in the case of supermassive black holes, can be catastrophic. Some of these cosmic titans are surrounded by vast amounts of general matter they feed upon. Others chew on stars that venture too close to the event horizon. Those stars get shredded by the immense gravitational influence of the black hole before becoming dinner. In both cases, however, eventual matter around the black hole forms a flattened cloud, or accretion disk, with the black hole sitting at its center. This disk glows intensely across the electromagnetic spectrum because of the turbulence and friction that the black hole's intense tidal forces create. Not all of the matter in an accretion disk is fed to the central supermassive black hole, however. Some charged particles are channeled to the black hole's poles, where they are blasted out as near light-speed jets that are also accompanied by bright electromagnetic radiation. As a result, these ravenous supermassive black holes sit in regions called active galactic nuclei, or AGN, powering quasars that are so bright they can outshine the combined light of every star in the galaxies around them. Furthermore, not all supermassive black holes sit in AGNs and act as the central engines of quasars. Some aren't surrounded by a wealth of gas, dust, or unfortunate stars that get too close. This also means they don't emit powerful bursts of light or have glowing accretion disks, making them much trickier to detect. Sagittarius A star, with a mass equivalent to around 4.5 million suns, just happens to be one of these quiet, non-ravenous black holes. In fact, the cosmic titan at the heart of the Milky Way consumes so little matter it is equivalent to a human eating just 1 grain of rice every million years or so. When this supermassive black hole does get a little snack, however, this is accompanied by a faint X-ray flare. That's exactly what the team set about searching for in 10 years of data collected by NuSTAR from 2015 to 2024. Michigan State University's Grace Sanger-Johnson focused on dramatic bursts of high-energy light for the analysis, which provide a unique opportunity to study the immediate environment around the black hole. As a result, she found 9 examples of these extreme flares. Sanger-Johnson hoped that by building up this bank of data on Sagittarius, A star flares, she and other astronomers can analyze the properties of these X-ray flares and infer the physical conditions inside the extreme environment of the supermassive black hole. Meanwhile, her colleague Jack Uteg, also from Michigan State University, was looking for something fainter and more subtle around Sagittarius A star. Uteg examined the limited activity of Sagittarius A star using a technique akin to listening to echoes. Looking at almost 20 years of data, he targeted a giant molecular cloud near Sagittarius A star known as the Bridge. Because clouds of gas and dust like this that drift between stars don't generate X-rays like stars themselves do, when astronomers detected these high-energy light emissions from the Bridge, they knew they must be coming from another source, then being reflected off this molecular cloud. The light echoing from the Bridge took hundreds of years to travel to it from Sagittarius A star, and then took another 26,000 to travel to Earth. That means by analyzing this X-ray echo, scientists has been able to begin reconstructing the recent cosmic history of our supermassive black hole. In other words, current findings will lead to further investigations, and those results have the potential to revolutionize our understanding of the supermassive black holes and their environments. Last, as a piece of good news, the hunt for gigantic cosmic monsters may be about to heat up. Here are 10 of the most extreme black holes that scientists expect to be able to observe. The gravitational range, or event horizon, of these black holes is about 5 times the distance from the Sun to Pluto. For comparison, these black holes are 2,500 times as massive as the black hole at the center of the Milky Way galaxy, whose event horizon is 1/5 the orbit of Mercury. 2. The smallest black hole. The smallest black hole discovered to date may be less than 3 times the mass of our Sun. This would put this little monster, officially called IGRJ 170913624, near the theoretical minimum limit needed for a black hole to be stable. As tiny as this black hole may be, it looks fierce, capable of 32 million kilometers per hour winds, the fastest yet observed from a stellar mass black hole by nearly 10 times. 3. Cannibalistic black holes. Black holes devour anything unlucky enough to drift too close, including other black holes. Scientists recently detected the monstrous black hole at the heart of one galaxy, getting consumed by a still larger black hole in another. The discovery is the first of its kind. Astronomers had witnessed the final stages of the merging of galaxies of equal mass, so-called major mergers. But minor mergers between galaxies and smaller companions had long eluded researchers. Using NASA's Chandra X-ray Observatory, investigators detected 2 black holes at the center of a galaxy dubbed NGC3393, with one black hole about 30 million times the mass of the Sun and the other at least 1 million times the mass of the Sun, separated from each other by only about 490 light-years. 4. Bullet-shooting black hole. Black holes are known for sucking in matter, but researchers find they can shoot it out as well. Observations of a black hole called H1743322, which harbors 5 to 10 times the mass of the Sun and is located about 28,000 light-years from Earth, revealed it apparently pulled matter off a companion star, then spat some of it back out as gigantic bullets of gas, moving at nearly a quarter the speed of light. 5. The oldest known black hole. Within GNZ 11, a galaxy in the constellation Ursa Major, astrophysicists have discovered the oldest black hole, weighing in at a few million times the mass of the Sun. It lives at the galaxy's center and is wolfing down matter at a time more than 13 billion years ago, or just 400 million years after the Big Bang. The James Webb Space Telescope spotted signs of the black hole's glowing accretion disk with NIRCam, the telescope's primary camera. The find highlights one of the biggest unanswered questions in astronomy: how the first black holes formed at all. 6. The brightest black hole. Although the gravitational pulls of black holes are so strong that even light cannot escape, they also make up the heart of quasars, the most luminous, most powerful, and most energetic objects in the universe. As supermassive black holes at the centers of galaxies suck in surrounding gas and dust, they can spew out huge amounts of energy. The brightest quasar identified to date is J043947.08 plus 1634115.7, which lies about 12.8 billion light-years away from Earth. 7. Rogue black holes. When galaxies collide, black holes can get kicked away from the site of the crash to roam freely through space. The first known such rogue black hole, SDSSJ0927 plus 2943, may be approximately 600 million times the mass of the Sun and hurtle through space at a whopping 9.5 million kilometers per hour. Hundreds of rogue black holes might wander through the Milky Way. 8. Middleweight black holes. Scientists have long thought that black holes come in three sizes, essentially small, medium, and large. Relatively small black holes holding the mass of a few suns are common, while supermassive black holes, millions to billions of solar masses, are thought to lurk at the heart of nearly every galaxy. One more massive than 4 million suns, for example, is thought to hide in the center of the Milky Way. However, middleweight black holes had eluded astronomers for years, until 2009. That's when scientists discovered one of the first intermediate mass black holes, called HLX-1, or Hyperluminous X-ray Source 1, approximately 290 million light-years from Earth. The mysterious object appears to be about 20,000 solar masses in size. Medium-sized black holes are thought to be the building blocks of supermassive black holes, so understanding more about them can shed light on how these monsters and the galaxies that surround them evolved. 9. Fastest spinning black hole. Black holes can whirl the fabric of space around themselves at extraordinary speeds. One black hole called GRS1915 plus 105 in the constellation Aquila, the Eagle, about 35,000 light-years from Earth, is spinning more than 950 times per second. An item placed on the edge of the black hole's event horizon, the edge past which nothing can escape, would spin around it at a speed of more than 536 million kilometers per hour, or about half the speed of light. 10. Tabletop black holes. Black holes are thankfully quite far away from Earth, but this distance makes it difficult to gather clues that could help solve the many mysteries that surround them. However, researchers are now recreating the enigmatic properties of black holes on tabletops. For instance, black holes possess gravitational pulls so powerful that nothing, including light, can escape after falling past a border known as the event horizon. Scientists have created an artificial event horizon in the lab using fiber optics. They have also recreated the so-called Hawking radiation thought to escape from black holes. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.